You know, right now, we're living through two absolutely massive technological revolutions at the same time. You've got the explosion of AI happening right here on Earth, and then you have the incredible expansion of our entire civilization into space. And what's so wild is that these two worlds, well, they're about to collide, creating something totally new, a kind of intelligent, thinking network right up there in orbit.
I mean, just picture the satellites orbiting our planet as we speak. What if they weren't just, passive pieces of equipment? What if they were active, intelligent machines? Satellites that could fix themselves when something goes wrong, assemble brand new things in the vacuum of space, and even make their own decisions. This isn't some far-off science fiction plot anymore. This is the next frontier.
So the big idea that's driving this entire shift is a concept called OSAM. It stands for On-Orbit, Servicing, Assembly, and Manufacturing. Now, for decades, our whole model for space has been launch and leave, right? We send a satellite up, and when it breaks or just runs out of gas, it becomes another piece of space junk. OSAM completely flips that script. It's about turning orbit into a place where we can actually build, maintain, and sustain everything we put up there.
OSAM really breaks down into three key pillars. Okay, so first up, you've got servicing. Think of this like a robotic mechanic in space, one that can refuel a satellite or swap out a broken part to keep it going for years longer. Then there's assembly. This lets us build absolutely massive structures, like new telescopes that are just way too big to ever launch from Earth in one piece. And finally, you have manufacturing, actually 3D printing new parts and components directly in orbit. This could slash our reliance on sending up expensive resupply missions from the ground.
Now, this whole concept isn't exactly brand new. I mean, we've technically been doing on-orbit repairs since 1984, and who could forget the famous Hubble servicing missions? But the game has totally changed. With mega constellations from companies like SpaceX putting up literally thousands of satellites, and commercial services like Northrop Grumman's Mission Extension Vehicle already out there working, the need for smart orbital management is more urgent than it has ever been.
But here's the thing. To make all of this actually work, to have a robot that can figure out what's broken, manufacture a replacement part, and then perform some incredibly delicate repair all by itself, well, that takes a staggering amount of intelligence. And that's where the second revolution comes into play. The brain for this orbital future, it's being built right here on Earth.
And if you want to get a sense of just how big this intelligence engine is, just look at this number, $5.4 billion. That's how much the US data center GPU market was worth in 2024. Alone. This is the hardware, the raw muscle, that is powering the entire AI revolution.
And when you dig into that market, you see a really critical trend. Over half of it is now made up of what are called inference GPUs. Now, put simply, these are the chips that run the AI models out in the real world. They're not the ones that just train them in a lab. What this tells us is that AI is moving out of the R&D phase and into a widespread, real-world application phase at an absolutely incredible speed.
This whole explosion has been supercharged by a model called High-Performance Computing as a Service, or HPC-AAS. In simple terms, it's basically democratized supercomputing. Instead of needing to build your own giant expensive data center, you can now essentially rent access to a global supercomputer whenever you need it, and you only pay for what you use. This has put world-class AI tools into the hands of everyone, from tiny startups to researchers and engineers all over the globe.
All right, and here's the pivot. This is the moment where these two huge trends finally converge. That immense computational power, the stuff that was perfected and scaled right here on Earth, is now leaving the planet.
And look, this isn't just speculation. This is happening right now. An NVIDIA H100 GPU, the exact same kind of chip that powers the top data centers on the planet, is scheduled to launch on the StarCloud-1 satellite. Just to put that in perspective, this single chip is about 100 times more powerful than any processor that has ever flown in space, ever. We are literally putting a data center into orbit.
So, the obvious question is, what does that actually let us do? I mean, what happens when you give our space infrastructure a brain of that magnitude?
Well, an incredible project called Oracle gives us a little glimpse into that future. It stands for Orbital Architectures for Cooperative Laser Energetics, and its goal is basically to turn satellites from a bunch of isolated islands into a single, interconnected, cooperative grid.
The Oracle project is built on three amazing ideas. First, using laser links for super-fast data transfer between satellites, which is already starting to happen. But the next steps are frankly revolutionary.
Step 2 is power transfer, using those same lasers to actually share energy and recharge each other in orbit. And then there's Step 3, momentum transfer. Light itself actually exerts a tiny physical push. Oracle wants to use focused beams of light to literally push satellites around, letting them maneuver and change orbit without ever using a drop of fuel.
And this is where it all clicks into place. With that on-orbit supercomputing power, these incredible ideas suddenly become possible. You can have fully autonomous robotic repairs. You can have intelligent, real-time space debris removal. You could dynamically reconfigure entire constellations of satellites to respond to a changing need on the ground. You could create, ultimately, a cooperative, self-sustaining infrastructure in space. The dream of OSAM becomes a reality.
But putting this much intelligence, this much autonomy into orbit, well, that brings up a huge new challenge. And it's no longer just a technical problem. It's a very human one. It's a problem of trust. You know, this is a major issue even for AI systems here on Earth. One survey found that a staggering 84% of global CEOs agree that for an AI's decision to be trusted, it has to be explainable. If a leader can't understand why an AI made a certain choice, they're just not going to rely on it. Now, apply that same exact logic to an AI that's controlling a multi-billion-dollar satellite.
And building that trust is really, really complex. To get to what we call responsible AI, we have to tackle some really tough questions. Who is accountable if an orbital AI makes a mistake? Is its behavior ethical? Can we really understand its decision-making process? Is this system actually secure from hacking? And does it operate without any kind of harmful bias? These are the questions that we absolutely have to answer.
Which really leaves us with this final, critical question. The technology to build these intelligent, autonomous machines in space is already here. The next great challenge isn't just about engineering the hardware, it's about engineering trust. As we create this orbital brain, how do we make sure that we can truly rely on it?